Yes, good evening, Doctor. This is Senoga Frank, and I'm going to present our research project. My research project was concerning traffic monitoring system. Um, this traffic monitoring system was about getting classifying objects from the data set which Madam you gave us. The video data set. So it was about detecting objects using YOLO and then performing classification using the various uh, convolutional networks. So I began with looking at a review of the deep learning models that are used in computer vision. I looked at the LNet. LNet, it is a convolutional neural network consisting of 5 layers with training parameters. So it has 3 convolutional layers and two other convolutional layers, making them to be 5. It accepts an input of 3 by 3 grayscale image with 1 channel, and it has a filter of 5 by 5 5 by 5 it's a size of 5 by 5. Yeah, it's a filter, 6 filters of size 5 by 5. Then there is what we call a mobile net. A mobile net was built, it's a convolutional neural network that was built on the principle to be used on resource constrained devices such as mobile phones. So these are neural networks that are developed to run on mobile phones and low power devices. Then there is a ResNet. This is a residual neural network that used to solve the problem of vanishing gradient due to its structure. This type of convolutional network has what we call skip connections and residual blocks that help to combat or eradicate the problem of vanishing gradient. So as I was researching, I realized that one of the research gap that exists in one of these models, for example, a ResNet, it is the problem of the vanishing gradient. So how do we solve this problem? Now we implemented the GoogleNet. The other model, for example, GoogleNet has a problem of vanishing gradients. So when you implement this one, we shall be like solving the other problem of vanishing gradient that exists in the GoogleNet. GoogleNet has that problem of vanishing gradient. So when you introduce this model can be used to eradicate also of that problem as the part of the research gap that exists in these models. Then there's what we call a dense net. So this one is also a convolutional neural network that also it is caused by the vanishing gradient in its high-level network due to long distance between the input and output layer. So this one, it solves the problem of it works like the other. It works like the other, the ResNet, because this one also structure is almost the same. Well, it's almost the same because it has what we call a dense kind of convolutional neural networks that really combat the problem of the vanishing gradient. So it also has what we call dense connections. Dense connections are like more of the skip connections that exist in the ResNet. The GoogleNet, it is a network that was built by Google. It has 22 layers. and it was trained on an ImageNet dataset. The models which I implemented are those ones. I implemented a ResiNet, that is residual neural network, GoogleNet, LNet, and then Loyo version 8. But among these first three convolutional neural networks, a ResNet and a ReNet, those ones perform to the best. Yes, they perform to the best. And even Loyo, I ran 5 epochs. One of the problem is that when I was training this Loyo, it consumed a lot of computational resources due to the fact that each epoch required a minimum of 1 hour and 30 minutes. So it really consumed a lot of computational resources, and I could hardly run any other program on the computer. So dataset description, yeah, this the dataset that madam you gave us. I downloaded it from that site, and then I annotated this video using the computer vision annotation tool, and I generated that I used to develop this model. I generated what we call the 2 vehicles, that is Saloni cars and motorcycles. So these are the factors that I used to build the neural networks. So data pre-processing, this one I converted the images to grayscale images. Then I did what we call the minimax scaler, minimax scaling of the pixels, such that the pixels are in the range of 1 to 0, and then resize all the images such that they all have a uniform size of 22 by 224 pixels. So then I split the data into training and testing, whereby the 80% was for the training set, and then the 0.2 was for the 20% was for the training, for the test data set. And this one, the mathematical conversion of this, that is 176, is equivalent to 0.8 or the 80%. So 176, those are batches, 176 batches for training and 44 batches for testing. But now, after building the model, beginning with the ResNet, I built the model using the various libraries that are available in Keras and the TensorFlow. So after successful building of this model, I came up with this the performance metrics of precision, recall, accuracy, and F1 score. So ResNet had a high accuracy of 0.985. And then this is the structure of the architecture of the ReNet convolutional network, ReNet 5 CNN. As you can see, from the first layer has it accepts an image of 24 by 24 pixels. And then it uses what 6 filters, and then the second layer has what we call the average spooling, and so on. This is the validation loss and the accuracy curves for the unit. As you can see, the loss keeps on lowering. It keeps on lowering the loss, and then here it keeps on to increase the number of epochs. The accuracy keeps on rising even here as the number of epochs increase, the loss retard or decrease keeps on reducing. Then ResNet, they had great the model that performed to the actual even ReNet 5 performed well, and even this one. Actually, the 3 models performed well, but now the problem with the other model is the GoogleNet. It had an accuracy. It was, I think this is a mistake, an accuracy of 0.8 to something. Yes. So this is the ResNet. ResNet performed well. ResNet performed well. Performed well, as you can see from the performance matrices. The precision, recall, accuracy, and F1 score, the values are high. So the libraries which I used, those are the libraries, TensorFlow. This is the area under the curve of the area under the curve of the ResNet. This is the confusion matrix of the ResNet neural network. The Google Net, I think this one performed well, but now it had a low value of recall. It had a low value of recall, but this the ResNet performed well, and this performance actually shows us how ResNet has a higher degree of learning. The learning rate is very high. Identifying patterns within the data set has the greatest rate at which, due to its performance, the rate at which identifies patterns from the data set or identifies objects, it is really very high, as you can see from the accuracy. Google Net, this was brought by Google, the employees within Google, the researchers are the one who developed this neural convolutional neural network. This is the performance of the Google Net. The performance of Google Net across 5 epochs. Now the YOLO model, that is the some of the picture that shows how the YOLO model is performing. How the YOLO model is performing. So it detected objects. As I said, my class labels were 2 saloon cars and motorcycles. So as you can see, saloon cars are being detected. Saloon cars are being detected, as you can see, and then as you can see here, a motorcycle. YOLO is doing the function of detecting objects. So I ran this, I performed this, I trained this YOLO model using the Ultralytics libraries, to train, to initialize and import this model. The code will be available on GitHub, and you will see how and then this is the confusion matrix of the YOLO model, and this is the precision confidence curve. As you can see, the precision confidence curve, it is going high, illustrating a greatest degree of performance of this model. And this is a table showing the performance of the YOLO model across 5 epochs. As you can see, epoch 1, you see that for example, the value of precision was very low, and also the training loss was very high. But as the number of epochs kept on increasing, you see that the training loss keeps on reducing. It was 4, now it reduces up to 1. In the training loss, the training classification loss, it is also retarding. But the precision increased up to 0.89. Even the recall, it increased. Even the mean absolute precision at 50%, it also increased. So this is the performance of YOLO. I across 5 epochs. Each epoch was taking 1 hour and 3 minutes. It contained a lot of computational resource, and it really constrained the the device and the gadget because it could even slow down. So this is the comparison of the various performance across the five what? Across the three models, LNet, ResNet, and GoogleNet. As you can see from this slide, ResNet and ResNet version 5, these two performed well. Even this one performed well, but you see, and the value of precision on GoogleNet is even lower than this one. So this one outperformed. So that's what I can present in this point in time. I beg to stop there. Thank you so much, Doctor.